Have you ever thought that how big a space telescope can be built by humans? If I say we already have the ultimate biggest telescope available for billions of years, and we can see through it daily. Yes, it's our sun, and gravitational lensing is possible through it. Sun's gravity can bend space-time, which bends light, and making it a big lens for us available all the time. Let's first clarify how gravitational lensing works, and then we will see how our sun can be used as a giant telescope. Einstein's general theory of relativity states that time and space are combined to form a single entity called spacetime. According to this theory, gravity is nothing more than the curvature of spacetime caused by massive objects. According to the theory, an object's mass will also cause a curvature in the path of the light as it moves through spacetime. Einstein's theory is demonstrated dramatically and observably by gravitational lensing. Spacetime is noticeably curved by extremely massive celestial objects, like galaxy clusters. They serve as gravitational lenses. In other words, a gravitational lens can form when a massive mass of matter, such as a group of galaxies, produces a gravitational field that bends and magnifies light from distant galaxies that are in front of it, but in the same line of sight. It has the same effect as looking through a very large magnifying glass. It enables scientists to examine the specifics of early galaxies that are too far away to be seen with current equipment and telescopes. When a single concentration of matter, such as the galaxy's dense core, is present at the center, gravitational lensing can take the simplest form. Around this core, a distant galaxy's light is redirected, frequently creating multiple images of the background galaxy. Einstein rings, complete or nearly complete circles of light, are created when the lensing gets close to perfect symmetry. More complex gravitational lensing arises in observations of massive clusters of galaxies. While the distribution of matter in a galaxy cluster generally does have a center, it is never circularly symmetric and can be significantly lumpy. Background galaxies are lensed by the cluster, and their images often appear as short, thin lensed arcs around the outskirts of the cluster. Now, these cosmological events has already been observed by Hubble and James Webb Space Telescope. A proposed idea is to use Sun as a giant telescope. In order to construct such a telescope, detecting equipment would be positioned at a location in space where the Sun's gravity concentrates lensed light from far-off stars. Future space telescopes hope to achieve this crucial observation by creating images that show how the distant star and its exoplanet are distinct from one another. Furthermore, a much stronger magnification would be produced by using the Sun as a lens. Astronomers would receive 1,000 by 1,000 pixel images from exoplanets located 30 parsecs, or about 100 light-years, away instead of just 1 or 2 pixels. With a resolution of about 10 kilometers on the surface of the planet, better than what the Hubble Space Telescope can see on Mars, we would be able to distinguish continents and other surface features. A similar super telescope would enable spectroscopy of an exoplanet, allowing us to determine the gases that make up its atmosphere. Exoplanet research would advance significantly, and habitable planets, and possibly even signs of life, could be found. The gravitational lensing technique has the advantage of being able to find planets that are roughly as far away from their central stars as the Earth is from the Sun. Other techniques are biased toward planets that are less likely to be habitable because they are so close to their stars. However, a gravitational lens telescope would need the Sun, Earth, and the star-planet system being observed to be perfectly aligned. Subscribe now for astronomy, cosmology, and science updates.